Welcome back to ME3121. Today we're going to start a new chapter, chapter 14, on vapor-gas mixture. Now here are some very common life scenario you probably have seen already. On the top left corner you have a cold glass of water, but on the outside of the water you have some water as well. You notice that the cup is not broken, but where does water come from? On the outside wall of the glass. Or another scenario on the top right, you have on a cold winter night and you turn on the heater inside of your car, and then you start to notice there are some moisture actually formed inside of your window. And another scenario is you're just sweating in a very hot summer day or just after an intense exercise. That's actually your body mechanism help you to cool down, but why you have to sweat maybe more likely in one environment than the other environment. And then the last picture on the top right or the bottom right corner is the foggy weather. You probably have all seen it, but where does fog come from? What is fog? So all of these scenarios have one thing in common, that is the relation between water vapor inside the atmosphere air. And the key word here is humidity, moisture, or condensation. So that's the topic we're going to discuss in this chapter. And particularly we're interested in water vapor inside of the atmospheric air. And now whatever we learned in chapter 3, although we felt it was very abstract, a lot of equations, they're going to come in play handy, because we're going to discuss water as an ideal gas inside of the atmosphere air. So let's take a look. So we call atmospheric air, so that would include water vapor and dry air. And when we talk about dry air, that just means air without any water vapor. For dry air, we already know it equals to, you can calculate the enthalpy, and that equals to Cp times T. For this case, for the range that we're discussing, we pretty much can treat air as a constant Cp, and from there we can calculate H, which will be heavily involved in the energy we're going to calculate. Now, as I mentioned earlier, we're going to treat water vapor inside the air behave as its stand alone, and it obey the ideal gas relation. So we're going to treat water vapor as ideal gas in this case. So how can we do that to treat water as ideal gas? Because you probably know the majority of the air we have is nitrogen, probably 79%, and 20% is air, and the rest are distributed into CO2, maybe some hydrogen. So the water vapor content is actually very low, so that just means the water vapor molecules are actually really far from each other. This is not very dense. And we can even treat air at the 1 atmospheric pressure, which is the environment we live in. Air alone can be treated as ideal gas. So it's not too far an assumption to assume water vapor also behave like an ideal gas. And then since they're ideal gas, and we can say the total pressure, whatever we call atmospheric pressure, consists of two parts. One is the dry air pressure and one is the water vapor pressure. In this case, we're only really interested in water vapor. We're not interested in other vapor. So even though we'll probably just simplify, call it vapor, but you know it's we're talking about water in this case. And for an ideal gas, we know that enthalpy is only a function of temperature. So this will be also very handy. Although this is just an assumption for water, but for the range that we're interested in, like negative 10 degrees C to 50 degrees C, which is pretty much the range that human beings live and that we're interested in, this is actually a very good assumption. Therefore, we can use the to calculate Hg, so water vapor enthalpy equals to Hg at 0. So we choose a reference point, which is at 0 degrees Celsius, and then use that to plus the Cp times T. And Cp in this case, we treat water as ideal gas, and we got a Cp average for 1.2. And we actually can compare the enthalpy of water using the table versus using the H equals to Cp times T, and then you find out they're actually very close to each other. So we didn't really sacrifice too much of the accuracy. So now we can define the concept of humidity. So first, the concept is called absolute humidity, or it's a specific humidity. So this is a ratio, that's how much water in per unit of dry air. So in this chapter, we like to use the term specific as respect to dry air mass. So it's how much dry air. So pay attention to that. The reason we're using it instead of using the total mass is because the water vapor will change, the amount will change, and if it condenses, then the water will leave, the vapor will leave the air, and that causes the total mass drop as well. So the water is going to affect the total mass too much, and it just makes the calculation way too complicated than it needs to be. On the other hand, when we discuss moisture, humidity, the dry air side doesn't really change, so that makes the calculation much easier. So that's why in this chapter we like to discuss things, the specific enthalpy, entropy, or any other terms we use per unit of dry air mass. So same thing here, we define the absolute humidity as a ratio of mass ratio, mass of water vapor divided by mass of dry air. And then because we treat both as ideal gas, we can have a relation of this as a pressure ratio. So that's much easier because usually it is really hard to measure the mass of water vapor inside, same as the mass of air. So it's really hard to measure, but pressure is relatively easy to handle. And then we can have, using the total pressure, substitute the P air to get this formula. So this is a very handy formula for calculation. So when we call the air is saturated, that means the air cannot hold any more water vapor. So it's saturated with moisture, and if you add any little more water, it will condense. So it will not stay in the vapor form. So then we call this air is saturated. And the picture on the right kind of show you what's going on. So when you have a dry air, then the pressure of vapor is a partial pressure of the total air, right? So it's the pressure of the vapor is 0, which makes sense by definition. Dry air has no water vapor in it, so PV equal to 0. When it's saturated, then PV equals to P sat at 25. So this number, if you see here, it's actually P sat at 25. So at if at 25 degrees Celsius, and you say the air is already saturated, then that means the PV equals to 3.1698. And if the PV is less than that 3.1698, then the air is not saturated yet. But if you try to add more water and to increase PV, you can't because anything you introduce will condense, and so the water vapor pressure will remain the same. It kind of capped there because you introduce more moisture, and then it will condense, it become water in a liquid format. Just imagine the cold glass of water, and then the water cannot stay inside the air anymore. It will condense, and so it will leave the air. So I like to think PV as, because we're talking about ideal gas, right? And in the last chapter, we said the PV ratio for the mixture is the mole number ratio, right? So you can think like that is like a mole fraction. So that's just show you how much percentage of the water vapor actually inside of the air. And then another concept is called the relative humidity. And this is actually the number you constantly hear in the weather report. They say, oh, today's humidity is 30%. So you don't hear it says it's 0.00145 kilogram of water per kilogram of dry air, right? So in the news or in the weather report, they use a percentage. And so what is that percentage? It says it's a relative, so it's defined as the vapor pressure compared to the vapor pressure when the air is saturated. So at a certain temperature, just so you know that how much air can hold water depends on the temperature. So at a certain temperature, the maximum amount of water vapor it can hold is a set number. So that number is P set at that particular temperature. And at this moment, you probably have a little less than PG. And then you take the ratio of it, it gives you the relative humidity. So you can think if your number is at PG, then you have 100% humid, because anything beyond that, the air cannot hold. The water going to come out as liquid. So whatever you have currently, then it become a relative number. So relative to the maximum. So definition is the mass ratio, but because we have the ideal gas, then you can treat it as a pressure ratio. And then you can, based on the ratio, you can work out the relation between relative humidity and the absolute humidity from either way to the other. So for example, on the right, this blackboard shows you, so if you have 25 degrees Celsius, 1 atmosphere, your air mass is 1 kilogram, your vapor mass is 0.01, the total is maximum the air can hold is 0.02, then the specific humidity or the absolute humidity is 0.01 divided by 1. So it's a mass ratio over the per kilogram dry air. But relative humidity equals to 0.01 divided by the maximum mass that it can hold. So it's 50%. So this just illustrates the difference between absolute and relative humidity. Now, quick question at the bottom. What is the relative humidity of dry air and saturated air? You should be able to answer this question. Based on definition, dry air has no humid, so relative humidity is 0%. For saturated, based on definition, should be 100%. I hope you get the right answer. After we define the relative and specific humidity, now we can calculate the enthalpy. Like I said, this is going to be playing an important role for calculating air conditioner and mixing all that devices. So we need to calculate the specific enthalpy. So enthalpy is defined by two parts, the dry air part and the water vapor part. And that equals to the mass of dry air times specific enthalpy of dry air plus the mass of vapor times HV. Now, specific enthalpy of the mixture equals to total H divided by MA. So pay attention, we're going to divide it by the dry air mass. And then two parts. The first part gives you the HA, the enthalpy of dry air, plus the ratio, MV over MA, which is defined as the specific humidity, times the HV. Now, HV in this case, the vapor, because it's in the vapor format, we can just approximate it as the Hg at that temperature, and then we can rewrite this formula H equals to HA plus omega times Hg. Now let's take a look at this example to see how we can apply those concepts to calculate them. So this problem gives you the room that contains the air, that give you the temperature and the pressure of the room, and they give you the relative humidity is 75%. Find partial pressure of dry air, specific humidity, enthalpy per unit mass, and the masses of dry air and water. So you're given the relative humidity, then you know you can calculate the specific because you have that equation. How do you calculate the partial pressure of dry air? Well, you know the partial pressure of dry air add the partial pressure of vapor equals to the total pressure. If you can find out the pressure of the vapor, then you can find pressure of the dry air. Pressure of vapor, like I said earlier, the relative humidity gives you the ratio of, let's write it, give you the ratio of PV over Psat. So Psat is maximum amount that this air can hold, so it's a function of temperature, and Psat at 25 degrees C. So then you're already given phi equals to 75%. You can calculate PV. So let's look up the table to find out Psat. So 25 Celsius. So you go to the saturated water temperature. Then you find Psat is 3.1698. So we write one more step. Psat at 25 is 3.1698. So that means PV equals to 3.1698 multiplied by 75%. That gives you 2.38 kilopascal. So that's the amount of vapor pressure. So the air pressure is just total pressure minus vapor pressure. Total is 100 minus 2.38 equals to 97.62. Next one, calculate the specific humidity. We have one equation, which is omega equals to 0.622 phi Pg divided by P minus phi times Pg. well, you can plug in the number. PG is the Psat at 25 degrees C, or you can just use what we already calculate, because phi times PG is PV. So this is actually PV. So you already calculate PV, you can just plug in that number. Or you can, based on definition, omega equals to 0.622 times PV over PA. Again, in the previous question, you already calculate PV and PA, so you can use those results as well. So let's do that. It's simpler. 0.622 times 2.38 divided by 97.62, 0.0152 kilogram of water vapor per kilogram dry air. So make sure you get the unit correct. Next question. The question asks you to calculate enthalpy. Now, enthalpy, we're not given the total enthalpy, so we need to do it separately, use the specific enthalpy for each part. So it's HA plus omega times HV. And HA is the enthalpy of air. We're going to use Cp times T, and HV, we can check the table, or if you want to use the other one, you can use the Cp of water vapor multiplied by temperature as well. So we can check the table for Hg at 25 C. So here's one thing I want you to pay attention. We can use the formula Cp times T, because for all the, at least for all the questions in this chapter, for all the air conditioner, humidity question, we set these T to where your enthalpy to be 0, because remember we need a reference, right? Because the technical equation should be delta H equals to Cp times delta T. Now, where is your reference? So in all the air conditioner humidity questions, the H T equals to 0 degree actually is set to be 0. So we actually choose that reference. So you will notice in this case, I'm not plugging in the absolute temperature for multiplying by Cp. I'm actually using the Celsius to multiply by Cp. It's just a reference change. I guess it's just for convenience, and people in this industry actually just for convenience to choose air 0 degree to be 0 enthalpy. But it's just not going to match with if you say calculating a turbine problem. So just keep that in mind. And you will see this number, whatever you multiply Cp times T, is not going to match what you're going to, if you check up the table for air enthalpy at 25 degrees Celsius, and you will notice this number would not match either. So it's really because of the reference point. So then I can plug in number for Cp of air, 1.005 kilojoule per kilogram Celsius times 25 degrees Celsius plus omega, which is calculated 0.0152 times Hg. Hg, let's look at the table very quickly. Hg at 25 is 2546.5. And you calculate this, gives you 63.8 kilojoule per kilogram dry air. So you would have to always carry the unit as per kilogram of dry air. Last one, to find out the mass of the dry air and the mass of the water vapor. So we're just going to use the ideal gas law. Ma equals to PAV RA divided by T. Now V is the total volume. In this case is the room volume. So V equals to 5 by 5 by 3 equals to 75 meter cube. So PA we already calculate, plug in 97.62 kilopascal, 75 meter cube. R is 0.287 for dry air, kilopascal meter cube per kilogram per Kelvin times 298. Notice here this is the ideal gas law. Temperature, you gotta use the absolute temperature in this case. Unit all got canceled. You're left with kilograms, so 85.61 kilogram. You can do the same thing for MV, which is PV times total volume RV times T. Now remember, the vapor of water vapor and the air are both inside the same room. Like we mentioned in the last chapter, these are gas. So gas is going to expand into the whole container. In this case, it's the whole room. So it will take up the whole room volume. So that's something different from solid or liquid. If you have a cup of water, it's not going to fill up the whole room. But if you have a cup of, say, a container of gas, you open the gas, it will spread out the whole room. So that's something you want to pay attention. So the volume is the same as the dry air volume, which is the room volume. Plug-in number 2.38 times 75. I know the unit's going to be the same, so I'm going to skip a little bit. RV 0.4615 times 298. So that's 1.3 kilogram. Well, on the other hand, you actually could have just used omega times MA. That might be actually faster. If you don't know RV, you couldn't remember what RV is, you can also use omega times the dry air mass. And so you can also calculate that way. Now let's talk about an important concept that's called dew point temperature. So this is the temperature at which condensation begins when the air is cooled at a constant pressure. So just think of this scenario, say the outside of your house at night, the temperature drops, and in the morning you start to see that there's some dew formed on the leaf. So that's a very common scenario. And during night, the temperature just dropping at a constant pressure, right? Because our pressure is the atmospheric pressure. It doesn't really change. But the water vapor, the mass, the amount of mass inside the air doesn't change. As the temperature start to drop, the air can hold less and less water inside. Remember we said earlier the total amount or the maximum amount of water that can be held in the air determined by the temperature. So you probably already know the hotter the temperature is, you can actually hold a little bit more moist. If the temperature drops to really low, it can actually hold less. So as a night comes, the temperature starts to drop and the air can hold less water. At one point, the water inside the air becomes saturated. So it becomes the maximum. And then as the temperature further drops, then more water start to condensate. So water will leave its vapor form to become liquid, and leaving the air to be still saturated air. So inside of the air is still saturated, you still have 100% relative humidity. If temperature keep dropping, then more water will condensate. And so that's what you see at the, like a leaf blade, or sometimes at night if you have heater inside, then outside or the inside of the window, you start to see it, because that's like at the window area, the temperature is actually cooler. So when the hot air reach there, water start to come out. So that temperature, when the condensation start to happen, is called dew point temperature. So this is a very important concept. So dew point temperature is the saturation temperature of water corresponding to that vapor pressure. So remember, we said originally, let's look at the TS diagram on the right. So originally you have a 0.1 and it has a certain amount of vapor pressure. At T1, the temperature was relatively high, so the air was not saturated. And then the air temperature start to drop along this constant pressure line. At one point, it dropped to that low, the air start to become saturated. And that temperature is the dew point temperature. And if you keep dropping the temperature, then the line will start to follow these saturated vapor line, because like we discussed earlier, if you keep dropping the temperature, water will come out, but inside the air is still 100% humidity. It still reach its maximum humidity. So it's going to, if you keep dropping the temperature, then it's just gonna follow this line, the saturated vapor line. So that explains why your cold glass will sweat, so to speak, or the cold soda will sweat. It's because the soda is really cold, and it's less than the dew point temperature of that air. So the air have some moist, and once it hit to the cold surface, the temperature locally dropped, and the air can no longer hold that amount of water, so it starts to condensate, and that's when you see the water droplet form outside of the can. And the dew point will probably tell you about humidity better than the relative humidity, because that sometimes you actually feel really hot. It's not because the temperature is high, but it's because the amount of moist that it can hold, it's too high, and your body cannot sweat enough because the outside is also very moist, so you just feel really hot when it's humid. Because you sweat to let the water evaporate off from your body, and you already know when water evaporates, it will absorb heat, so that cools your body. But if outside is also very humid, then your body cannot, the water cannot evaporate quickly on your body, so it cannot cool your body enough. So that's why you feel, let's say it's 90 degrees, but 90 degrees in California is different from 90 degrees in Florida. So that's the reason. So let's look at the fogging on the window scenario. So this is the scenario where we said, okay, inside the house was really hot, maybe at night, and then at the window area it's actually colder because it doesn't block the temperature as well as a wall. So at the window it actually is cooler. So as the hot temperature inside the room start to reach to the window, and in this case, we have a relative humidity of 75%, then the question asks you what is the window temperature so that the dew will start to form on the window. So basically it's asking you the dew temperature, right? The dew point temperature. Because if it's cold enough, then water will start to condensate. And so, but how cold it needs to be. So it just means at that temperature, whatever moist amount you have right now inside this house will become the saturated vapor pressure. That means, so your dew point temperature is Tsat at that vapor pressure. So we need to find out what is the current vapor pressure in the house. We're given the relative humidity, and we already know that pretty much indicate the vapor pressure, or in regards to the saturated pressure at that temperature. So at this point, it's 20 degrees Celsius. So PV equals to phi times Psat at 20 degrees Celsius. That's a definition for the phi, right? It's the PV, the current vapor pressure, over the maximum pressure of, or the maximum amount of vapor that the air can hold, which is the Psat at that certain temperature. So 20 degrees Celsius, Psat is 2.3392. So that would give me 75% times 2.3392 kilopascal. That's 1.754 kilopascal. So this is how much amount of water vapor in the house right now. And then that would corresponding to what temperature? So let's take a look of the table again. So 15 degrees C, Psat is 1.7. Now it's 1.75, so that means the temperature will be slightly above 15. So it's you would do an interpolation between 15 and 20, but you know it should be very close to 15. So you can do an interpolation, say 1.754 minus 1.7057. So this is corresponding to your dew point temperature minus 15 equals to the next one is 20 degree. So you solve for the dew point temperature is 15.4. So that is the Tsat at 1.754 kilopascal. Okay, hopefully now you can explain why on a cold day inside is warm, so you would form the water droplet inside of the window. But if you, on the other hand, if you are on a very hot day and you turn AC on inside, say, your car, and you're driving, and if the outside is kind of moist, then it will start to form condensation on the outside of your windows, just like how the moist air form dew overnight. So the dew point temperature is an important concept, but dew point temperature isn't that easy to measure directly. But we are interested in to measure the humidity of any unsaturated air, right? So how did we actually do that? Nowadays, you probably have all the electronic devices, you can measure it, but what is the principle behind it? So let's take a look at this adiabatic saturation process, which will provide as a principle for measuring the specific humidity or relative humidity. So here in this device, I have a box here. It's insulated, so there's no heat transfer between what's inside the box to outside the box. At the inlet 1, I have some unsaturated air coming in with a specific humidity that I don't know, and this is the one that I'm interested in calculating. And there are some water liquid provided here, and the liquid water has a lower temperature than the air, T1. So the water will evaporate into the air, and when the air leaves the box, it will become saturated air. So this is an adiabatic situation. So we can say the heat transfer only happened between the air and the water. So based on this setup, we can actually set up some formulas to calculate. So here's how it goes. We will set the mass equation and the energy equation. Let's look at the mass first. From the mass coming in from 1 and leaves to 2, we separate them into dry air and water. Dry air mass never change, okay? So when it comes in from 1 and then it leaves to 2, so no air mass change. But water is different. Originally, I have a certain amount of water, so let's call it m dot W1, and then it will absorb some liquid water into the air mixture. Then it leaves as saturated, so when it leaves we call it W2. So we can set up this equation, and we also know that m dot W1 equals to omega times ma based on definition. Then we can find out our first equation, m dot F, the supply water amount over dry air mass, equals to omega 2 minus omega 1. Now look at the energy equation. We said this is an adiabatic box, and so all the heat transfer happened between the air mixture and the liquid water. So the air that coming, or the energy that coming into the box is Ma times H1, the liquid carried by the Mf, and when it leaves, it becomes H2. And remember, the H was defined based on per unit of dry air, so we multiply by m dot A, and so you can divide it by m dot A, and notice here we got this liquid mass over the dry air mass again, so we got a second equation. Also, we can further expand H1 into two parts, the air part, Cp times, or Cp air if you want to be very specific, times T1 plus the omega 1 Hg1, that's the water vapor part, and H2 can expand it also two part, air part and the water part. Now we have we can plug 1 into 2, and if you notice here in the H1, H2, I can pretty much find everything except for omega 1, right? Because Cp is air, we know. T1, T2, we can actually measure. Hg1, Hg2, we can also measure. Omega 2, we already know it's 100%, so because we know Phi2, so we can actually calculate with here, it's provided here. Then we can express omega 1 in this equation after sorting out all the above formulas. So with that, we can actually calculate omega 1 if I do have this type of setup. But nobody's going to use this setup, this type of setup. So what but this gives people an idea to create a device that can do something similar. So that device doesn't really work well in practical purpose. And so practically what people do is they just find a regular thermometer and cover the top with some wet cotton. And so the cotton is soaked in water, and then they put it on the top of the bulb. And then you can imagine, because the evaporation of water to the surrounding air, the temperature will start to drop. And at one point, it can no longer drop because the local atmosphere is kind of saturated. It can no longer take more water. So this is similar to the adiabatic process that we just looked earlier. And this temperature we measured is called wet bulb temperature. And contrasted to that, we have the dry bulb temperature, which is pretty much, as you see, it's when you don't have this wet cotton. Whatever temperature you measure in the room, it's the dry bulb temperature. So that's where these terms come from. So we can use this wet bulb temperature to approximate the adiabatic saturation temperature. So the case we just saw in the previous slides, the T2 when it exits from that channel. So people designed this sling psychrometer to use it to measure the wet bulb temperature. So this device was actually first invented in 1600. So it's such an old device. People are still using it today, even though there are electronic version of it. It's probably much faster doing it. But because the electronic version require time to calibrate, it actually required quite a long time to calibrate, just I guess because the water need to evaporate completely on the sensor. So this sling psychometer actually still work in place. So let's check it out how it actually works.
So today I want to show you how to use a sling psychrometer and how to determine relative humidity and dew point. So a sling psychrometer is an instrument that meteorologists use. There are basically two thermometers. One's called the dry bulb, one's called the wet bulb. You notice that there's a sock at the end of the wet bulb thermometer. Okay, we want to figure out how much moisture is in the atmosphere and how much evaporation is going to take place. Okay, you can see that both thermometers are about 25 degrees Celsius. What I'm going to do for the wet bulb is I'm going to take a beaker of water. I'm going to submerge the sock into the water. Okay, now evaporation is going to be a cooling process here. So I want to see how much evaporation is going to take place within this air mass today. So now I'm just going to take the two of these. I'm going to spin them around. Now the spinning increases the wind. Wind ultimately will cause evaporation to happen at a faster rate. The faster evaporation, the more cooling on the wet bulb. Okay, so after spinning for about 5 minutes, okay, our dry bulb and our wet bulb, okay, clearly see, this is my wet bulb here, has dropped down to about 18 degrees Celsius, while my dry bulb is still at about 25 degrees Celsius. Okay, what you're going to do is you're going to take your dry bulb and your wet bulb and you're going to subtract them. And that's going to give you your wet bulb difference. In this case, we have a difference of 7 degrees. Now you're going to use the dry bulb and the difference to get your relative humidity and dew point. So when you come to your chart in your reference table, you can clearly see that your dry bulb, which is along the left side here, you go in between 24 and 26. That's going to give you a 25 degree dry bulb. Go to a difference of 7. 0, 1, 2, 3, 4, 5, 6, 7. So you end up having a difference of 7. You're in between 12 and 15 degree dew point. So relatively dry air today. So let's just say, for instance, we have between 12 and 15 let's just say that that's a 13 degree Celsius dew point for today. And then for the humidity, you do the exact same thing. You find between 24 and 26, there's a 25 degree dry bulb. We're going to go to a difference of 7. 0, 1, 2, 3, 4, 5, 6, 7. Between 49 and 51%, we have a humidity today of 50%. So that's how you use the sling psychrometer and how you use the dew point and relative humidity charts in your reference table. We'll talk to you soon.
And that's pretty much how it works. That device, surprisingly, as much as you think it looks very old school, it's actually pretty accurate. And you notice you have to use a reference table to figure out the dew point temperature and the relative humidity, which we're going to try to calculate them first. So those tables based on the equation I just showed you earlier. So let's see how we can use whatever we measure. So this video just gives you an idea what is the sling psychrometer actually look like, how it works, and what is the dry bulb temperature and what's a wet bulb temperature. So hopefully after this video you have a better idea of what these things are. So let's take a look of how we can use that dry bulb, wet bulb temperature to actually measure or calculate the relative humidity and some other parameters. So you use the sling psychrometer to find out dry bulb 25 degrees C, wet bulb 15 degrees C, and find out specific humidity, relative humidity, and enthalpy. So I already listed this equation out here. So that's the one we're going to use. So specific humidity, that's the omega-1 that we need to calculate. Remember that adiabatic process, you coming in as 1, here's a liquid supply, and then the air leaves out as 2. So remember that setup. And in this case, the dry bulb is the temperature coming in, 25, and the wet bulb is when it's saturated, so that's the T2 is 15 degrees Celsius. And so then we can just plug into that formula. So let's take a look. We need to calculate omega-2 first, and so let's look at omega-2 equals to 0.622 Pg2 divided by P2 minus Pg2. Pg2, basically that's the saturated pressure at 2, right? So because 2 is saturated. 15 degrees Celsius, saturated pressure 1.7057. So we can write Pg2 is Psat at 15. So that is 1.7057 kilopascal. And P2 is just the atmospheric pressure is given there. So we can plug in number 0.622 times 1.7057 divided by total pressure 101.325 minus 1.7057. Calculate omega-2 is 0.01065 kilogram of water per kilogram of dry air. Now we can plug in omega-1. Omega-1, remember that Cp is for air. We need HFG2. So HFG2, let's see, 2 is 15 degree HFG, 2465. Need HG1, which is HG1 is 25, so HG1 2546 and HF2. HF is 15 degrees Celsius, so that's 62.982. And then we can plug in that formula. We know Cp is 1.005 kilojoule per kilogram per degree C multiplied by T2 minus T1. T2 is 15 minus 25 plus omega 2, 0.01065 multiplied by HFG2, 2465.4. So you know the units will be kilojoule per kilogram now on the top. And on the bottom, HG1, 2546.5 minus HF2, 62.982, also kilojoule per kilogram. So they should cancel. You will have a ratio in the end that is 0.00653 kilogram of water per kilogram of dry air. This is the first question. Second question asks you to find out the relative humidity. So you know we have the formula to convert between specific to relative. So that is omega 1 P1 divided by 0.622 plus omega 1 PG1. PG1 is Psat at T1, which is 25 degrees C. So you can check the table, 25 degrees C, 3.1698 kilopascal. Plug in 0.00653 times P1. P1 is the total pressure. So pressure in this case never really changed, right? It's just the atmosphere pressure. And divided by 0.622, 00653 PG 3.1698. That is 33.2%. So relatively low. Last one asks you to calculate enthalpy. So enthalpy at the of the air is, or the air mixture, Cp T1 plus omega 1 Hg1. So Cp is that term is air, 1.005 times 25. Omega 1 we calculated 0.00653 times Hg1 we found out earlier, 2546.5. Total gives you 41.8 kilojoule per kilogram of dry air. So you can imagine that each time you measure the wet bulb and dry bulb, and if you have to plug in the equation to calculate omega, to calculate relative humidity, to calculate H, it's a tremendous amount of work, and especially if you have to do this all the time, and you probably figured, why don't we just have a chart? Like what the video shows, you can actually refer to a chart to read relative humidity instead of doing this calculation. So especially back then, you didn't have a computer, you can't just punch in the number and automatically receive an answer. So that's why people created the table or chart. So let's take a look. So what we have is called psychrometric chart, and this is constantly used in the air conditioning application. So it's much easier just to read the table instead of doing the calculation every single time. The typical chart will look as on the left. So on the x-axis, you have the dry bulb temperature. Y, you have the specific humidity. And from there you have the saturation line. So these are the curved line. And for all these curved line, we have a certain relative humidity. And then you have a white bulb line. You have H line and a specific volume line. So those are the lines we have, and notice the T wet bulb is pretty much parallel to H, just because H is a function of temperature, so that these two are actually pretty close to each other. Some charts actually just have one. And this chart is very similar to whatever our property chart before, or those tables, is when you have two intensive property, then you can determine all the rest. So for example, if you have dry bulb and you have the wet bulb, and you can imagine whatever dry bulb temperature it is, it can cross with the wet bulb line, and then that means the state of that air mixture is set. From there, you can read all the other properties from that point. So you can find all the other parameters from there. So just keep that in mind. You're always looking for two parameters to determine the state, and then you can find the rest of them. And on the right, it just says on the saturation line, your wet bulb, dry bulb, and the dew point temperature are the ones. So this is how you find out your dew temperature, is when you have the saturated state, and if whatever the wet bulb read or the dry bulb read is the dew point. So let's take a look at an example to show you how you can actually read the chart. So please, so this chart gives you the temperature, which would be the dry bulb temperature, and 40% relative humidity. And from there, we can see how we can read everything else from this chart. Notice here, the problem also mentioned this is at 1 atmosphere pressure. So each chart is for a specific pressure. So pay attention to that. Most of our problem probably won't cause any trouble, because all of our table just have one ATM. That's the only chart. So if you don't have one ATM, then you got to go back to use those equations we did in the previous example to calculate. So just keep that in mind in case any problem that come up that is not 1 atmosphere, and you cannot, in that case, you cannot read this chart anymore. So let's take a look. We have dry bulb 35. So dry bulb temperature is on the x-axis, so 30 and 35, so this is 35. And we have relative humidity 40, so let's cross these two lines. So this point will be our state of this mixture. So the first question asks you to read omega. So omega is on the right hand side. So now you draw a flat line to the right. And it's above 14, so this is 14, and this is 15, this is 16, so that means it's between 14 to 14.5, so we'll call it 14.2. Notice the unit here is gram per kilogram dry air. So if we want to use our usual unit, which is kilogram water per kilogram dry air, we need to convert. So we found omega equals to 14.2 gram per kilogram dry air. which is 0.0142 kilogram of water per kilogram dry air. So this is the first one. And then from there, it asks you to calculate enthalpy. So remember, enthalpy is those tilted line. So the H is pretty much parallel to the wet bulb. Looks like this point is on this dash line already. So I'm just going to draw this on the dash line and cross with the entropy line. So this is 70 and here is 80, and there are 10 grids in between. That means each grid is 1, so this looks like 72. So we can say H equals to 72 kilojoule per kilogram of dry air. The next one asks you to find out the dry bulb. Looks like our point is already on these dash line. The dash lines are the dry bulb temperature. So this line, the blue one I'm highlighting right now, is the 25 degrees C. And let's see what's the next one. So the next one is 20. So 20, 21, 22, 23, 24, 25. So looks like our point is on the 24 line. So the wet bulb temperature is 24 degrees Celsius. Now, how do we find out dew point temperature? Earlier we said dew point temperature is the same as dry bulb temperature, as wet bulb temperature when it's saturated. So when is this mixture going to become saturated air? So the saturated, you can think like this. My water content in the air is not going to change. So omega is not going to change. Omega constant, which means it's a flat line, horizontal flat line. So I'm going to draw this flat line to the left. So you can think this process as the temperature keep decreasing until it reach to the 100% saturation line. And from there, whatever the wet bulb temperature or dry bulb temperature will give you the dew point. Because the dew point is not showing directly on this chart, right? So yes, you can read, say this is between those two dash line, maybe it's between 19 to 20. You can guess from there, or you can just simply draw another vertical line to read the dry bulb line. That's usually probably the easiest way than to read the wet bulb line, because the arrow between those are a little bit bigger than the dry bulb scale. So that's 20, and the one next to it is 19, so it's in the middle. So let's call it 19.5. So the dew point temperature is 19.5. So this is important. Make sure you know how to read the dew point temperature from this chart. And lastly, it asks you to find out the specific volume. And the specific volume is these green lines that is tilted a bigger slope. So this is 0.92, 0.9, 0.88. So this point looks like a little bit above 0.89. So looks like this line is 0.89. So we can just call it 0.892, specific volume 0.892 meter cube per kilogram dry air. So this is also useful later on when you calculate how much air you need to mix, and the volume is actually going to play a role to calculate the flow rate. So this is the example of how to read this psychometric chart. Make sure you practice and know how to use it. This is going to be example, and this is the foundation for all the rest of the example of this chapter. So let's stop here today, and next time we're going to look at a lot of examples that involve in cooling and heating and air conditioner. So I'll see you next time in the video.